Okay, so we've done a lot on differentiating. We've used it to find gradient functions, to find tangents. We've used it to find stationary points and evaluate maximum and minimum values. Because we've done so much work, we should be quite familiar with what the derivative of a function looks like. So if I know how to find the derivative of a function, then it's pretty easy to go the other way and say, well, if I know the derivative, then I can find the original function. So that process is called anti-differentiation. You're going back the other way from differentiating. And the original function is denoted with this capital F, and it's called the primitive. So what this means practically is that if I know that the derivative of x squared is 2x, then x squared is the primitive of 2x. So it's going back the opposite way. But here's a question for you. What's the derivative of x squared plus 3? 2x. What's the derivative of x squared minus 5? Well, that's also 2x. So if I give you a function and ask you to find the primitive, is that enough information? We'll show you in a minute how to deal with that question. So, looking here, you've got a function. If I give you a function x and I say to you, what is the primitive of that function? So the primitive of x, well, if I was to differentiate, I would take 1 away from the power. So if I'm going to do the opposite and find the primitive, I obviously need to add 1 to the power. So I'm going to get x squared. But think about that. What happens when you differentiate x squared? You get 2x. I only have x. So if I started with x squared over 2 and differentiate that, I would get x. Well, what about x squared then? What's the primitive of x squared? So I can add 1 to the power, I get x cubed, but again, if I differentiated that, I would have 3x squared, and I only have x squared, so I need to take a third of that, because then the 3's will cancel each other out. Similarly, what about x to the power of 3? Well, add 1 to your power again, x4, because if I differentiate x to the power of 4, I get 4x cubed, but I only have x cubed, so I need a quarter of that. Are we picking up on a pattern yet? So what if you were given this function, 5x squared minus 3x plus 4? Well, let's think about that. The 5x squared should have started as a 5x cubed, but then I need to take a third of that to account for the 3. And then I've got 3x, so that should have started as an x squared, but I have to put that over 2. What about plus 4? What's the primitive of 4? Well, what do I differentiate to end up with a constant? X. So that's the primitive of 5x squared minus 3x plus 4. In general, this is your rule. So you've got, if the derivative is equal to x to the n, then y, your original function, is x to the n plus 1, all over n plus 1. Now we've got this plus c here. This is plus c. This is what accounts for that idea that I don't know whether I started with that original function x squared, or if I started with x squared plus 3 or x squared minus 5. It's accounting for the fact that they all have the same derivative. We just add a constant on. So, what does that mean? Alright, well here's our examples. If the derivative, f dash x, is equal to 2x, and the original function passes through the point 2, 8, we want you to find the original function. Alright, so this is the way we go about it. Start off with your derivative. So we know that that's equal to 2x. So if I was to find the primitive of that function, well, I know I would have x squared. So you take your power up. Now in this case, I would generally be saying, well, over 2. 2 over 2 is equal to 1. They've cancelled each other out. Okay? And then I say plus c, plus some constant, because I don't know whether I started off with x squared plus 1, x squared plus 5, x squared minus 4. It could be anything there. I'm not sure. I've got some constant that's acting on this function. But what I do know is that it goes through the point 2, 8. So what I do is come back and say, well, when x equals 2, I know that function 2 is equal to 8. That's what they've told me. So substitute them in. 8 is equal to 2 squared plus some constant. So 8 is equal to 4 plus some constant. My original function, c, had to be equal to 4. Okay? So therefore, the original function, the primitive, was x squared plus 4. Because if I differentiate x squared plus 4, I get 2x, which is what was given to me, and that's the one that passes through the point 2, 8. Alright, so let's have a look at another one. The gradient function of a curve is 3x squared minus 2x. The curve passes through 2, 1, find its equation. So what curve was that? Well, they've told me that, now you can use whichever notation you like here. You can use dy dx, you can use f dash x, it's up to you, whatever you're comfortable with, because they haven't given us one, so it doesn't matter. So 3x squared minus 2x. So I know that the primitive of that, the original function, well, it had to be x cubed, and then I'd put it over 3, and the 3 and the 3 would cancel out. And that one had to be x squared, because the derivative of x squared is 2x. And then I have my constant. But at x equals 2, y is equal to 1. So let's start substituting in. So 1 is equal to 2 cubed minus 2 squared plus some constant. So 1 is 8 minus 4 plus c. So what's c? Well, c has to be minus 3. So therefore, my original function, or the equation of this curve, is x cubed minus x squared minus 3. Because that would give me a derivative of 3x squared minus 2x, and it passes through the point 2, 1. Alright, so for this one, I want you to be doing exercise 211. For questions 1 to 4, do parts of it. How many? It's up to you. It depends how much practice you need. If you're cruising through this, don't worry too much. If you're struggling, do more. After that, then I want you to do the even numbers. Okay? So good luck, and I'll see you in class.